The next thing we want to talk about is the derivatives of sine and cosine functions. So here you see I've given you the graphs of each one here. So here's our cosine function, here's our sine, and we can see here that the relationship between the derivatives of one and the other are kind of related. So if we look at the derivative of cosine at 0, okay, what is that slope? Well, the slope is 0. And if we look at the sine function equals 0 at that point. Okay. Now if we keep going down, the slope right here actually is -1. And what's the height of the sine function here? The height is 1. Okay. Again, we can think, well, what's the slope of the sine function right here? Well, the slope of the sine function is 0, and then the height of the cosine function is 0. So there's some sort of relationship here. Now here, if we look at the sine function, the slope is going to be -1, and then the height of the cosine function is -1. Okay, so the slope is -1, here our height was -1. Here the slope is 0, here the height was 0. Here the slope was 0, the height was 0. What's the slope of this function? That looks like it's +1, and then the cosine is 1. So the way this works is the derivative of the sine function is the height of the cosine function. And the derivative of the cosine function is the opposite of the sine function. And you can spend a little more time if you want to try to see how that works right over here. But you can also memorize these. Derivative of sine is cosine. Derivative of cosine is -sine. So you will have to have those memorized. So let's go ahead and find the derivatives here. We have y equals 2 sine x. Okay. We know the constant is going to mean that this just stays as 2. And then the derivative of sine is cosine. So we get 2 cosine x. In letter B, try this one on your own. All right, you should have gotten cosine x over 2. And letter C, here, y prime. Well, the derivative of x is just 1, so this is that sum of derivatives here. And then the derivative of cosine x is, well, minus sine x. All right, so that is derivatives of sine and cosine function. Pretty simple. You just have to remember which one change a sign and which one doesn't. All right, our last topic for today is derivatives and rates of change. And the derivative can be used to determine the rate of change of one variable with respect to another. And it's actually what the derivative is. Now, if we recall, distance equals rate times time. The derivative is a rate, so we'll solve for rate here. So rate equals distance divided by time. Okay. Now, we can find the average rate of change. And this is something you've already done before. And we just let s of t be a position function of an object. So this is its position. And the average rate of change is going to be the change in its position over the change in time. And this is going to be the average velocity over that time period. All right, so an example. If a billiard ball is dropped from a height of 100 feet, its height in feet s at time in seconds t is given by the position function s of t equals -16t squared plus 100. So this tells us how high the billiard ball is at a specific time t. Now we want to find the average velocity over each of the following time intervals. So this goes from time equals 1 second to time equals 2 seconds. So an entire second elapses, we want to know what was the average speed over that time. So what we have to do here is find the position at time equals 1 and the position at time equals 2. So we're just going to plug 1 into our function for position. So we have negative 16 times 1 squared plus 100. And this equals 84. And then we have negative 16 times 2 squared plus 100. And this equals 36. So now we're going to use our average rate of change right up here, delta S, so the change in S, over delta T, the change in time. So delta S is going to be 36 minus 84. And so we're going to take the first one and put it second, and the second one and put it first here. Okay? And then the change in time, it goes from 2 seconds to 1 second. Okay? And again, it doesn't matter, I guess, which one you pick first, as long as you are consistent with which one you pick first. And this gives me negative 48 over 1, and this is going to be feet per second. Now, why is the velocity negative? Well, because the ball is dropping, so that's why we have a negative velocity there. So that's the average speed over that 1 second. Now what we're going to do is cut that time by half a second, so 1 to 1.5, and we want to find the average velocity there. So again, we need S of 1, which we already know is 84, and we want to find S of 1.5. So we're going to go negative 16 times 1.5 squared plus 100, and this gives me 64. So again, we're going to do delta S over delta T. So we have 64 minus 84 over 1.5 minus 1, and we get negative 20 over 0.5. And if we divide something in half, it's like multiplying it by 2. So this is negative 40 feet per second. I want you to go ahead and try C on your own. So find the average velocity in that 1/10 of a second, 1 to 1.1. Go ahead and pause the video and come back to check your work. All right. Welcome back. You can go ahead and check your work here. You should have got negative 33.6 feet per second. Now, hopefully you can see what's going on here. We have 2 seconds, 1.5 seconds, 1.1 seconds. What we're trying to do is let that delta T disappear. Now, if we let delta T go down to 0, we're going to actually find the actual rate of change, or actual velocity, at time equals 1. And it turns out, by letting this go to 0, all we need to do is find the derivative of our position function. So we would want to find S prime of t, which is negative 32t to the first power. So the instantaneous rate of change here is just going to be negative 32 times 1, which is negative 32 feet per second. And you can see here our limit as delta t went to 0 is getting closer, and it would have been negative 32 feet per second. So let's just say that S of t is a position function of an object. The instantaneous rate of change, or the velocity, is the derivative of the position function. So our function v of t is S prime of t. So an example, at time t equals 0, a diver jumps from a platform that is 32 feet above the water. The position of the diver after t seconds is given by negative 16t squared plus 16t plus 32. The first question, how long after the diver jumps will the diver hit the water? So if we think about this, here's all the water down here. You got your little diver. and this is your position s of t. So if he jumps off and he hits the water right here, what is the position? Well, the position is 0. So we want to know where 0 equals negative 16 t squared plus 16t plus 32. And this is algebra 2, just solving for a polynomial, for a quadratic. Looks like we can factor out a 16, a negative 16, so we have t squared minus t minus 2. And the negative 16 won't factor into our answer. Now we want to factor t squared minus t minus 2. So we have t minus 2, t plus 2. And this would give me the solutions t equals 2 or t equals negative 2. And we don't deal in negative time, so at time equals 2, okay, so it takes him 2 seconds to get down to the bottom. So what is the diver's velocity at impact? So we have to remember that the velocity at time t is the same as the derivative of the position at time t. So let's go ahead and find the derivative of this right up here. So we have 2 times negative 16, which is negative 32, and then t to the first, so t, and then here would be plus 16, and then plus 0. So all we're going to have to do is plug 2 into this equation. So we want s prime of 2, and that equals negative 32 times 2 plus 16, giving us negative 48 feet per second. So that is how we can apply this idea of derivative to some real-world examples. All right, I hope you feel comfortable with these rules, and thanks again for watching. We'll see you in class.